Orbital diagrams are just a different way to represent the electron configuration. Now, our orbital is going to be represented by a box, okay? So how many will each of the how many boxes will each of the orbitals have? Well, S just has one. P has 3 boxes that are all connected. D has 5 boxes all connected. And hopefully you're realizing that this corresponds to the number of orbitals for each per energy level. And then F has 7 boxes all connected. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, all right, so those are S, P, D, and F box. So now we're just drawing it out. We're going to make sure that we indicate our electrons with arrows. So the arrow is the electron. Each box can only get 2 electrons, and the electrons have opposite spins. So one spins up, the other spins down. So we have to make sure that we indicate that as well. All right, we're still going with the same ideas before of filling the lowest energy level first. Okay, so we always start with 1s. This is called the lazy tenant rule because people always want to be on the first floor before they want to climb to the, 7th floor with stairs and no elevator. All right, and we also have to contend with what's called the empty bus seat rule or Hund's rule. So basically, that says that when you have multiple sublevels per energy level, like in the P, Ds, and Fs, that each individual, let's back that up, okay? Each individual orbital, each box, will get 1 electron before anybody gets a pair. Empty bus seat rule. You always go to the empty seat first, and then if no empty seats are available, you go to the one with 1 of them. So you see here, it was filled based on 1 up, 1 down, which is not correct. Everybody gets 1, and then somebody gets a pair. So the second picture is the correct one. All right, so let's do the orbital diagram for oxygen. Oxygen has 8 electrons. The electron configuration is 1s2, 2s2, 2p4. Okay, so we draw a 1s box, 1 up, 1 down. And then we have a 2s box, 1 up, 1 down. And then we have a 2p box. Now remember in the 2p, you go 1 up, 1 up, 1 up before anybody gets a pair. Okay? And you see this matches directly with the electron configuration. So the exponent tells you how many arrows you use in your box. Okay? And then these correspond to the box. Remember, S only has 1 box. P has 3 connected. And then 1 up before anybody gets a pair. All right, well, let's talk about stability. When you think about this in terms of the orbital diagram, it makes a lot of sense. What would be most stable? Well, most stable is going to be any full energy level or any box that has everybody 1 up, 1 down. Everybody has a pair. The next most stable is going to be your completely full energy levels, even though maybe the entire energy level is not filled. Okay, so a full S, a full P, a full D, a full F. Now over here, what's special about this last row, this full energy level, is you have a full S and a full P, or in this case down here, a full S, a full D, and a full P. Okay, so that becomes very important. Then the full, and then the half full. Half full, you're talking about like having on the P orbital, you'd have 1 up, 1 up, 1 up. That's half full. Or D, you'd have 5 all going up. Okay, so they're all going in one direction. And this does affect stability. So most stable is a full energy level. Second most stable is a full orbital. So full S, a full P, a full D, a full F. And the third most stable is going to be half full orbitals.